Okay, so we're going to talk about probability today. So any happening whose result is uncertain is called an experiment. So anything we talk about now, we're just going to call it an experiment. The possible results of the experiment are outcomes. Okay? The set of all of the possible outcomes within the experiment is called the sample space. When each outcome is equally likely to occur, you sometimes have to distinguish between the choices or between the outcomes. So we'll keep that in mind if there's any overlapping or anything like that. So when you're asked to find the sample space, all you have to do is talk about what kind of outcomes are going to occur. So think about this situation. A six-sided die is tossed. What kind of answers are you going to get? What kind of outcomes are going to happen when you roll the die? 6 possible. What are they? Right. 1, 2, 3, 4, 5, or 6. So that's what you write. So you put a fancy bracket, and then you list all of the outcomes with commas in between them, and close your bracket. That's all sample spaces. So a coin is flipped and a die is tossed. So think about those outcomes. And you want to be organized about it because sometimes the lists are kind of lengthy. So if I flip a coin, I can either get a heads or a tail, right? So if I get a heads, I could get a 1 to go with it, or a 2, or a 3, or a 4, and so on, all the way through 6. But the other choice I have is that when I flip a coin, I get a tail instead, correct? So that's going to be tails 1 through 6. Okay? Close the bracket. It's all sample spaces. Just a list of all of the outcomes that you could get. All right, so now we're going to talk about probability. So really, what we're doing today is the same thing that we've been doing so far, except now we're just going to write it in terms of a fraction. We're in the fraction. The number of outcomes we want goes at the top over the total number of outcomes possible. Okay? If you get a probability of 0, it's called the impossible event. It just can't occur ever. Okay? If you get a probability of 1, it's called a certain event, and that means it's guaranteed to happen. So 2 coins are tossed. What is the probability that one will land heads up and the other will land tails up? Okay, well think about it. What's going on here? If you toss two dice, so here, not dice, coins, sorry. We're tossing coins. Could you get a heads and a heads? Or you could get a heads and a tails, right? But then you could also get a tails and a heads or a tails and a tails. Right? Those are the 4 scenarios. That is the sample space. So out of all of the possibilities, there's a total possibility outcome of 4. We want to know what's the probability that will land a heads up and a tails up. Well, isn't that these 2 situations? So out of the 4 situations, we're looking for 2 of them. So it's just 2 out of 4. You want to simplify it to get 1/2. You can either write it as a fraction, or you can write it as a percentage, or you can write it as a decimal. Any of those answers are acceptable. So you figure out how many events are happening that you want out of how many total events possible. That's all probability is. Okay, a card is drawn at random, this should say from, a standard deck of playing cards. So we kind of talked about the cards. What is the probability that a card is a heart? So before we move on, I want to talk real quickly. How many numbers are there within a suit? There's 13 total cards in a suit. How many of them are numbers? 10, 8, 9. Okay, I've heard 8, 9, and 10. Let's go through it. 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 9 numbers.
I know.
What's an ace?
A 1.
Oh, so I heard an ace is a face, an ace is a 1. Does an ace card have a face on it?
No.
So an ace is not a face. So an ace is not a face card. Does an ace card have a number on it? No, it has a letter on it. So it's not a number card. So an ace is just an ace. Okay, so an ace is a special card. There are 4 of them, 1 of each suit. Okay, there are 3 face cards in each suit. So there are 12 total face cards in the deck. Good for the scenario? We got this? Okay, so now what is the probability that the card is a heart? Well, first of all, what's in the sample space? How many cards total in the deck? 52. So that is our sample space. Now we want our scenario, our event that occurs. How many hearts are there in the deck? 13. So it's 13 out of 52, which simplifies to 1 out of 4. Makes sense that 1/4 of the deck is hearts because there's 4 suits. You could write this as 25% or 0.25. Questions so far? All right. Of the 1,354 people that graduated in 2000 from Canton High School, 672 are female and 682 are male. If a graduate is selected at random, what is the probability that the person is a female? Well, how many total in the sample space? Yep, 1,354. We're choosing females. How many females are there? 672. So 672 out of 1,354 is our probability. And we should simplify. So 336 over 677, which is 0.496 or 49.6%. Easy enough? Okay, so that's basic scenarios. All right, now let's talk about mutually exclusive events. So 2 events, A and B, from the same sample space have no common outcomes. Or they're known as the empty set. When this happens, these events are mutually exclusive. Okay, there is no overlapping between them. They have nothing in common. This is how you say this, the probability of A and B. So that little rainbow symbol is the and symbol. You could write the probability of A and B. So when that happens, A and B happening together, it's 0 because they have nothing in common. The probability of the union of 2 events. So if A and B are events in the same sample space, the probability of A and B occurring is given by the probability of A in union with B. So the probability of A plus the probability of B. Then you would have to subtract out the overlap. So this is subtracting the repeats. If A and B are mutually exclusive events, then the probability of A in union with B is just the probability of A plus B. If there's no overlap, there's nothing to subtract out. That's all that's saying. Here's the important piece right here. When you see or, you add. Okay, that's what you have to get from this whole thing. Okay, if you have an or situation, you have to add the probabilities. So, example 5. 1 card is selected from the standard deck of 52 playing cards. What is the probability that the card is either a club or an ace? So I'm going to find each of the probabilities, each of the event's probabilities, and then I'm going to add them together because I saw the word or. Okay? So, how many clubs are in the deck? How many clubs? 13, because that's a suit. So 13 out of 52 represents the clubs. Now I have to figure out the probability of an ace. How many aces are in the deck? So 4 out of 52. Is there overlap? Yes. What is it? The ace of clubs. And how many of those are there? 1. So 1 out of 52. So because this was an or situation, I add these probabilities together. But then, because I had overlap, I have to subtract that out because I don't want to count it twice. I'm already counting the club here and the ace here. So I don't want to count the ace of clubs again. So once you do that, you end up getting, what, 16 out of 52? So 4 over 13. All right. 2 fair 6-sided dice are rolled. What is the probability of getting more than 10? What does more than 10 look like? First of all, when it says more than 10, it's saying the sum of the numbers. So what does more than 10 look like? You could get what? A 5 and a 6, or a 6 and a 6, or a 6 and a 5. Notice we're saying or here. Okay, so what is the probability of getting more than 10? Well, how many choices do I have of that event happening? 3. How many in the sample space? Whoops. How many in the sample space? 6 on the first and 6 on the second. These are like mutually exclusive. They are not going to, like one doesn't, not mutually exclusive. One doesn't, they're independent, right? When you roll the first die, it doesn't affect rolling the second die, right? So because they're independent, you got to multiply those choices together. So we have 6 times 6, giving us 3 out of 36. Okay, so 3 were the choices that we had here when we listed it out, right? In the total sample space, there's 6 numbers on the first die, 6 numbers on the second die. They don't affect each other when you roll them, so you multiply those together to get all the choices, all the sample space. So 36 is a sample space. That's how many combinations are possible. And then 3 is what we're looking for. Okay, moving on. A committee of 3 is to be picked at random from a group of 5 girls and 4 boys. What is the, this should say probability, that the committee consists entirely of boys? So what's the probability that the committee consists entirely of boys? Now let's think about what's happening. Let's think about the sample space first. So I don't really care that there's boys and girls. I just care that there's 9 total people to choose from. Out of those 9 people, I'm choosing how many? 3, because I'm trying to form this 3-person committee. Now let's think about the word committee. Does order matter? No. So when I pick these people, is it a permutation or a combination? It's a combination because the order doesn't matter. So this is like merging 8.5 and 8.6 together. So out of the 9 people, I want 3 of them. This is the sample space. That's how many total 3-person committees can be formed. But I want a specific type of committee. I want all boys. So out of the 4 boys, how many of them do I need? 3. So that's going to be 4C3. Out of the 5 girls, how many do I need? 0. So times 5C0. Now technically, you don't need this 5C0, but I want you to see what happens here. That 4 plus 5 gives us 9. All right, that's the total in the group to choose from. And then the 3 plus 0 gives us 3 people in the committee. So you can always check your combinations to make sure you've added up to the correct total of what you need. You can just type this into the calculator. You could plug it into the formula. It's quicker to do the calculator. You get 1 out of 21. Questions? Okay, let's keep moving. All right, independent events. When the occurrence of one event has no effect on the occurrence of the other event, you must multiply the event's probability. So this is what we were talking about before. Do you remember that question about the true and false test? It was like a 10-question test, and it was true and false. So the way you answer question 1 doesn't affect the way you answer question 2 or question 3 or so on. Those are independent events. When you have independent events, you multiply. The key here, again, is when we see this word. So when we see and, we multiply. So you want this and this to happen, you just multiply the answers. I mean the number in the sample space. So example 8. A random number generator selects 3 integers from numbers 1 through 20. What is the probability that all 3 numbers are less than or equal to 6? Well, first of all, you got to think about what is a sample space. So if this number generator creates integers from 1 to 20, how many in the sample space? 20. There's 20 numbers. It's 20 minus 1 plus 1, so 20 numbers total to choose from. if we want a number that's less than or equal to 6, what does that look like? 6, 5, 4, 3, 2, 1, so 6 numbers. So 6 out of these 20 numbers represents the scenario that we want. But how many times am I going to pick those numbers? 3. Does one affect the other? No. It generates a number, then it generates a number, then it generates a number. None of them. Yes, because it's random. So because these are independent events, we want to multiply these situations together. So it's like it spits out integer 1, which is going to be 3 out of 10. I just simplified that. That's all. Okay? Integer 2 then, the probability is 3 out of 10. Integer 3, the probability is 3 out of 10. These are and situations, or these are an independent event situations, so all you have to do is multiply those together, giving you 27 over 1,000. Okay? See the difference between and or. Or you add, and you multiply. All right, last topic. The complement of an event. So the collection of all outcomes in the sample space that are not in A. It's denoted by A prime. So when you see this, this means not A. So when you have the probability of A and not A, shouldn't they add up to 1? Because you're talking about all of the possible scenarios. Either this happens or it doesn't happen. Okay, so those all add up to 1. So in order to figure out the not event or the complement of the event, you can do 1 minus the probability that the opposite of what you want occurs. Now, let's take a look at this. 2 fair-sided dice are rolled, not told. I don't know what's going on here. What is the probability of getting a total that is less than or equal to 10? So didn't we already figure out this probability, this kind of like the situation that's opposite this? If you go back and you look at the scenario that we talked about here, example 6, it says, what's the probability of getting more than 10? So more than 10, isn't that the opposite of getting less than or equal to 10? Right? This is talking about 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We were talking about getting an 11 or a 12. So we figured out the complement of this already. So the probability of not A in our scenario was 3 out of 36 or 1 out of 12. We've already done that part. This was getting more than 10, which is the opposite of this. This is a smaller probability to figure out. It's quicker to figure out this one because there's only 3 scenarios. So you can take 1 and you can subtract the opposite of what you want, giving you 11 over 12. Yes?
Could you just, like, if we didn't do that example, could you go over how you would go about doing it, like what you didn't find out the first?
I'm about to.
All right.
Yep. So, keywords to look for in this is like at least or not. Okay, those are good keywords to look for to know that you should do the complement. So now that did require us to do the one previous, but let's look at example 10. So the probability that it's going to rain each day this week is 20%. Find the probability that it will rain at least once this week. So right here is a good hint. Boys, if you can't be quiet, leave. When you see these words, at least once a week, this is a good indicator that you want to use complement, okay? Now let's think about this. The probability that it will rain at least once this week, so it could rain once, twice, 3 times, 4 times, 5 times, 6 times, or 7 times, right? That's a lot of possibilities, but then also think about what's going on here. Because of it raining 2 days, like it could rain a Monday and a Thursday, or a Wednesday and a Saturday, or Saturday and Sunday. So there are so many possibilities to have to think about here. It would be really hard to figure out that probability just straight. But if you figure out the complement, it'll be easier, because think about it. If it rains at least once, isn't the opposite that it doesn't rain at all? Isn't the only scenario not counted here is the 0, like it doesn't rain? Because it could rain once, twice, all the way up to 7, or it could not rain at all. So that's 0. So this is the non-event. This is easier to figure out. So now you want to think about that happening one time. So if it's going to rain 20%, that's a 20% chance, then what's the probability or the possibility that it doesn't rain at all? 80%, right? 1 minus the 20%, or like 100%, you know, minus 20% gives us 80%. So there's an 80% chance that it doesn't rain. So now think about this. It's like Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. So it doesn't rain on Monday. It doesn't rain on Tuesday. It doesn't rain on Wednesday, or Thursday, or Friday, or Saturday, or Sunday. That's the opposite of what we want. This is the complement. Is this an and or an or situation? Are these independent events? If it rains on Monday, does it affect it Tuesday? No. So that means we have to multiply all of those together. Isn't that the same as 0.8 raised to the 7th power? Right? But 0.8 raised to the 7th power is going to tell us the probability that it doesn't rain. We want the opposite of that, so we have to do 1 minus this. And our answer is 0.7902, or 79.02%. So what you do when you figure out the complement is, like, if it's too many scenarios to figure out, if it's too hard to figure out what they're really asking for, you can do the opposite of it. And then you think about that, and you subtract it from 1.